slideshow তো করে show slideshow তো করে automatic ভাবে ওটা activate হয়ে যাবে
The second page. This is the space. So reference for the and this page we have these nice pictures and where to start. Given teaching, pros and reject and reject funding. So first we should discuss why chromo. Quantum chromodynamics has the word chromo or color in it. We have to read word chroma, but spoiler alert is actually not quite color, but it's more closely assigned to something we can call strong charge or color charge. But why choosing color in the first place? Being a student of physics, we know that color comes from electrons popping through their orbits and it's emitting some frequency or particular light which we receive in our eye as color. So why choosing physics topic with such an abstract and absurd name? So let's think about the color theory first. We can see that the RGB coloring or subtractive CMY, salmon and the yellow colorings have this SU3 symmetry. There are three elements which make it white, which is a pretty strong analogical argument to make by assigning this to quarks. So let's have a look. Color charges SU3 symmetry. Here we can pretty much clearly see that quarks have colors. We have three quarks that has their colors which cancel each other out so that the hadrons are always colorless. Mesons are quarks which are particles which are composed of comprised of two quarks. Usually comes as quark and anti-quark color pairs, anti-color pairs, which you can see here. Red is countered with anti-red, green is countered with anti-green, and so on. The fundamental difference between QCD and QED is that this one, gluons have colors too. In quantum electrodynamics, we have seen that photons don't have electric charge. They don't interact with each other. But here, the problem starts here. Gluons do have colors and they do interact with each other, which we get back soon. So, what is QCD about? QCD is basically a primitive cousin of quantum theory that describes how quarks and gluons interact with each other, and it tells us about the study of the nucleons and their stability and why neutron, which is a neutral particle, have magnetic moment, and why we see no free quarks emitting. And this is an equation which requires pretty heavy math, which we can't really get, but still on taking a first observation from the equation, we can see that the left term we can have a psi f and to psi f denotes something which we can associate with the interaction of gluons and quarks, and the right term is the tensor, probably the gluon field strength tensor or something which is speaking about the gluon interactions, which makes it fundamentally different from QED. Look at the equation. This is the data that L is probably the Lagrangian density, and many books make a huge mistake here that when denoting proton or neutron, two upwards and one downwards, one upward and one downwards, they usually make the gluon strings away like circular gluon strings, which is wrong. We should always consider it in this way. Who cares? We should, because all the marks we see here, we, the camera, the board, the table, all the marks that we come to see doesn't come from the Higgs field. Many people have this huge misconception that every mass is derived from Higgs field. That's not quite it. So if we evaluate the mass of the protons in this pie chart, we can easily consider that the mass of protons, the 99% of it, comes from the energy of gluon and quark from the equal-statistical equation. Only 1% is the contribution of quark mass, which comes from the and there are some exotic matter. Sorry, my slides are little out of date. Okay, so exotic matter, which we'll get back later. There are states explainable with QCD, which takes account of matter states which are solid, liquid, gas and plasma, there are other states which can be considered from QCD like mixed phases where protons, neutrons, quarks, and gluons are share space, and quark gluon plasma and other exotic forms of matter. Strange quark matter and other forms. So is it working? What if it's wrong? It's not quite. In 1964, as one of my friends mentioned earlier, one element proposes the existence of quarks and experimental hadrons. Independently, also there like George Spike, and in 1973, David Gross, Franz Wiechek, and David Kruszel, you can see three of them, Bolinza, Gross, and Wiechek, proposing a key concept to quantum thermodynamics known as the asymptotic freedom. But still, scientists were not quite sure about it. What if it's wrong? So in 1979 in Petra, Daisy, Germany, it was confirmed by three gentlemen, the famous three gentlemen, we will get back soon, which discovered the gluons. And in 2000, we also in CERN, RHS and LHC, the quark gluon plasma state was observed. This state we will get back to that soon also. This is a state very crucial when studying the beginning of the time, when the universe was in a baby stage. We will get back to that soon. So key concepts. Here we have a little meme image for that. We have asymptotic freedom, confinement, symmetry of key concepts, and this meme demonstrates on a quark which is in short range thinking that he has freedom, which is asymptotic freedom, but actually if we get the bigger picture, it's just gluon offering him freedom in imprisonment. It is imprisoned in the confinement, it's trapped in hadrons forever. So let's discuss asymptotic freedoms. It's probably my design fault, so see can know. So these are a series of experiments which contributed to this alpha S. This is actually a coupling constant, which is proposed to run inverse of the law of Hughes. I'm not going to maths because I myself can not go that far. But we can see from here that many of the data matches, and that proposes that in very short range or high energy, quarks behave almost like free particles. In the Dyson standard model, Gross's standard, he discussed this about UG-3. Similarly, for confinement, in low energy or longer distances, quarks are trapped in hadron field. Think about it in this way. Think about it like when we have a rubber band and we try to squeeze it. It's pretty easy and it takes almost no force, and you can squeeze it as far as you want. But when you want to stretch it out, it resists. This property is a key, and when you push really hard, it snaps out. The same happens for here. If we have quarks want to excrete, want to take out a quark from any hadron or state two quarks really high, see if we can get a free quark or so on. What we get is a quark antiquark pair, and it snaps, and we get two particles instead. This is discussed in Ira slavery in Susskind chapter. And this VR sigma probably comes something from the mathematical concepts of Wilson's loop or some sort of thing like that. That's we can see that the potential is constant width. So experimental proof. Here comes the interesting part: the discovery of gluons and quark gluon. So experimental proofs. Here the fun part starts. The discovery of gluons and quark gluon plasma. This is actually fascinating stuff. This image is a historical image of the 3J event of Petra. You can see the third jet, and it was a really celebrated image throughout the particle physics community. And this image is also a celebrated image in the astrophysics community also. This is an image of the beginning of the universe. We can see that the first part, the preliminary parts, when the universe was just born, a billion of seconds, there was this state called the quark gluon plasma, you can see from here. And the discovery of gluons. In 1979, at the Petra collider at Daisy, Germany, physicists observed this particular 3J events. This is a really celebrated event. Usually, a positron and an electron, when annihilating each other, produces something called Z bosons and other particles. But very few times, they occasionally produce this quark and quark pair, and which comes along with a gluon. This is the celebrated event. And for quark gluon plasma, under extremely densities, you see in RIC and you can see the electrons melt into quark gluon plasma state where quarks and gluons share states. Means it's the counterpart, it's the most superlative part of the plasma state where protons and neutrons move freely with electrons, breaking atomic bonds. It breaks the proton-neutron bonds and it goes purely as a quark gluon plasma, a hot dense soup. This and we can see in this diagram here the variable density increases and temperature increases. The higher temperature parts are achieved in LHC and RHC, and the recent studies from LIGO and Virgo which discovered gravitational waves and neutron stars, we have this data and we have a pretty clear concept where the electrons remain and where the proton stars. It's also the most perfectly known because it has almost zero six. So, is it relevant to the world? Yeah, it is very much. The proton mass puzzle, the mass of proton discussed earlier, the mass of protons comes not very little from the mass of quarks, but rather the interactions and the quark-quark interactions and the energy of gluon and the factor of energy. The Young-Mills mass gap problem, also known as the Clay price problem, the millennium price problem. This is really theoretical stuff. Glue ball, which we have mentioned earlier, gluons do interact with each other. So why don't they form completely explicit particles which are completely comprised of gluons? We are naming that glue balls. That's bound state interacting gluons. And this Young-Mills theory actually a mathematical theory one, which will these glue balls, if proven right, will give a huge insight, and it's a linear particle right now. Neutron star groups. Here things get really tricky. We see tons of things here. We see some suggest that we see color superconductors where matter carries color charge without loss. In similar ways, where conventional superconductors, the Cooper pairs and so on, behave like almost impermeable, which scientists argue. Strange quark matter, a form of matter hypothesized to be more stable than normal matter, made of strange quarks. Mixed hadron quark physics, where hadrons like protons, neutrons share phases with quarks and gluons. This is a more deeper insight into the inside neutron star. We have some pretty convincing diagrams, which some suggest that part will be a color superconducting quark matter, but it's not discovered yet. So it's an active study topic. We have the extraordinary core of a neutron star, where we can see not only a quark core but also a hyperon core where nucleon-like particles made of strange quarks can be seen. The chaos condensate core, some of my friends have discussed chaos very explicitly earlier. We might be able to see these phases in neutron star. So current understanding of QCD. There are a lot of methods in the non-quadratic methods. Some methods involve CHPT, but we are presently discussing the lattice QCD method, which is like making. We have a pretty nice and brief understanding of the quantum center physics and lattice. We know lattice is very good. So why not use this concept to study QCD? This image, what it shows is one very important thing. If this is a core of a proton or a neutron, we can see there are 5 particles, more than 3. But if we look really close, we can see that they cancel each other out. They come in quadratic pairs. This sometimes happens in QCD and we don't quite see all of them coming out. There could be a charm core inside a proton, but we will never see it because it will cancel each other out. It appears and reappears maybe. There are many possibilities in the study of lattice QCD, where we use supercomputers with machine learning probability. And yeah, this here is have a provision for extra special dimensions. It's already a 4D lattice, so we can, if we keep adding more extra dimensions, it becomes very close to the natural state we want to get. So there does have a provision for string theory. The hypothetical theory we scientists have been discovering for over 50 or 70 years, but not quite sure about because there is no proof of it. Okay, so summary, it's also a neat picture that sums up. Color charge doesn't have any color. It's not real color, it's actually color charge. Interactions are not quark and quark only. Gluons do interact with each other. The mass function described in this funny image of diagrams, I think it's a pretty historical comic. When someone says that Higgs field gives us all our mass, and that slaps it with ever heard of QCD. Asymptotic fundamental pain